Welcome to HDR Tarpini. My name is Timothy Lottis, and this is the Neokino Graphics channel. This talk is responding to this WCCF tech interview. The HDR gaming interview, veteran developer explains its sad state and how he's coming to its rescue. I'm going to, however, voice the counter-argument, why you should not support the HDR standard and what the alternative is. Let's rewind time, and I'm going to bring back some data I measured back in 2016 I presented in my GDC VDR talk. This one is looking at how the room environment actually affects what you get for real contrast on your display. And so I had a bunch of different rooms that I went to and a bunch of different lighting situations at different times of day. One of them was 1000 nit ambient, and then all the way down to a 0.05 nit ambient at the end. And then based on if you had a 400 nit screen in that environment and you knew what the reflectance was on the screen, so somewhere between, say, 1 to 8%, it would tell you how many stops of contrast you have in that environment, like real contrast, like what you see as black and then what you see as white on the physical display. So in that first room with lots of light, that one you'd only get 2.3 to 5.3 stops. And then by the time we get to the last room, which is one that's really dark, you get anywhere between 16.6 to 19.6 stops. Now I will note that this last one's kind of a fake one. It was actually measured, meaning I had a 100 nit ambient display, and I measured a 0.05 nit ambient level in the room being lit by that display. But then I did the computation as if I had a 400 nit screen, which is not exactly right. I would have to remeasure the ambient level with a 400 nit screen, which I didn't have at the time. But anyway, the takeaway from this is that the room environment is the primary thing that determines what the screen looks like. This idea that the display needs to do tone mapping because HDR added something, it's really a marketing scam. For instance, in the example QD-OLED panel we're going to talk about later, there's only a 2-stop difference between the SDR to HDR modes. And that's the SDR stable mode to the peak HDR mode. It's only a 1-stop difference if you take HDR mode against the unstable SDR with global dimming enabled. And so this particular display would have a real contrast ratio with room reflection somewhere in the neighborhood of 9 to 12 stops. Now we compare that whole thing of 1 or 2 extra stops for HDR against a 15-stop difference in viewing environments. That's pretty extreme. So again, viewing environment has the primary contribution. And then another point here is, like, back in 2026, I measured my Sony Vega CRT TV, the one I still use today, and this thing had a roughly over 14 stop contrast at low APL. And the way I actually measured that was with a puck, so it's isolating the tube from room reflection, meaning that if this thing is in a really dark room and it's not pumping out much brightness, so you're not getting much ambient level, and you have very, very low ABL, it's going to have pretty high contrast. It's going to have contrast that is effectively like an HDR display. In fact, the thing that limits the Sony Vega is the blooming in the tube. Otherwise, this thing has great contrast. In a dark room, of course, because, this is a glass screen, it has some decent reflection. So my point here is that high contrast existed long before anybody labeled TVs as HDR. I kind of forgot that high contrast existed because LCDs replaced CRTs and we had these horrible LCDs for a long time. So these HDR TVs didn't actually change the situation that we were in. The fundamentals existed before HDR TVs. We never needed a new standard. Let's talk about HDR LCDs. There's really nothing good here. They have horrible uniformity artifacts. Either the black levels rise in the zone, the dimming zone, or the peak brightness drops if you, say, only have a few dots of HDR. Not to mention, PC displays often have amazingly poor static contrast, say like 10 stops. And then they're leaning on bad uniformity to fake the extra range. And then to top it off, these displays have bad gray to gray time or bad overshoot. Basically, you pick your poison, one or the other. Now let's take an example WOLED and let's talk about the reality of the panel. Now some of these I'm rounding to get even numbers, but the point still stands. This example display is roughly 1000 nit peak at 1% APL and about 250 nit peak at 100% APL, which means a white screen. So the panel is just getting 2 stops extra brightness as APL drops. That's not that much. However, the RGB contribution tops out at 250 nits, and it's all the W subpixel element to get to 1000 nits. Thus, the wide gamut actually ends around 250 nits. When you're going up in these larger stops, the last 2 stops, you're basically blending out to about 25% of your gamut by the time you hit the peak. Now, SDR with the global dimming enabled supports almost 500 nits. And of course, that last 1 stop is blending towards 50% gamut. If you choose the stable SDR mode, now you're getting 250 nits peak, roughly, and you get the full gamut. You can toggle that on and off independently. So personally, I'd rather use the stable SDR mode with the wide gamut toggle. This has roughly 13 to 10 stops of dynamic range, depending on the ambient level in the room. Why would I increase another 2 stops when I have to accept such bad behavior? Now let's talk about a QD-OLED, an RGB OLED. This is also rounded up again to make the conversation easy to understand. This one has none of the gamut loss of the WOLED panel. Roughly 1000 nit peak at 2% APL and a 500 nit peak at 10% APL and 250 nit stable peak at 100% APL. So we're talking a similar trade-off, roughly 2 extra stops, but it's unstable because it depends on the variability of the APL. So note that to do shader BFI with the phosphor decay, the technique I talked about in another talk, that requires high APL. So again, I'd rather just use the stable SDR modes with the wide gamut toggle. I already have 12 to 9 stops depending on ambient in this display. I don't really want the bad behavior that comes with adding 2 more stops of contrast. Another thing we should address is that PQ is actually a horrible standard. First off, it requires expensive shader code to target correctly. If you're going to do the linear to PQ transform, it's expensive to do it properly. So one reason you do the linear to PQ transform is if you actually want to do correct dithering. I really talked about that in my VDR talk, so I'm not going to repeat it too much. It's a pretty complicated concept because the amount of banding changes across the tonal curve. So you can't just use one small amount of grain. You have to adjust the amount of grain depending on the amplitude of the signal. So PQ typically requires 10-bit instead of 8-bit. So you're getting 20% less peak display FPS. It also wastes a bunch of the encoding space for non-displayed highlights because the encoding space is absolute 10K nits, which is really not true. And typically I might have, say, a 1K nit display, or maybe something that's only 250 nit in its stable configuration. It wastes a bunch of the encoding space for Rec 2020 gamut. The displays are a smaller P3 gamut. It also shifts the banding into the mid-range where it's more visible. I'd rather have banding in the darks where the other is more perceptually okay. In my VDR talk, I presented an example of what you get at different PQ maximums against Gamma 4, Gamma 2.2, sRGB, and Rec 709. And you can see at 3 bits per pixel, you can see pretty clearly the banding is actually a lot worse than the PQ modes. You're way better off, say, using our sRGB or Gamma 2.2. So I'd rather have any of these over PQ. Gamma 2, which is amazingly fast in hardware to encode with proper dither. Gamma 2.2, the old standard, slightly more expensive, it works well. sRGB, slightly more expensive yet, and less good in the darks, but it's not necessarily as good as Gamma 2.2, but still better than PQ. Note all of these, we can use standard spatial temporal blue noise that can target well at 8 bits per pixel. In fact, I've targeted at 6 bits per pixel and it looks fantastic. Thus, I would rather have the full encoding range used for the actual display output. And I don't want the toddler retone mapping the signal in the display. So the right alternative, use the SDR interface. Use the display's wide gamut or native gamut toggle. That'll give you the full gamut in SDR mode. Use the display's stable SDR mode to disable all the cheating. So that's about it for today. There's nothing really game-changing about HDR standards, other than the amount of trouble they have caused for developers and in the industry. Not supporting the bad standard is perhaps the better solution. It's the solution that I'm going to do.